Hope you are all are doing fine. Now today we'll start a topic of infinite series with positive term. It is a topic of real analysis from UPSC paper 2. This topic comes in the paper 2 of the maths optional, and it is infinite series with positive term. Firstly, congratulations to all those students and aspirants who are able to clear this prelims examination 2023. But enjoy, have fun for a day, for today. But remember that this is just a first phase, okay? And it is a rat race here, so you should be doing your level best, okay? You have gotten the opportunity to write the mains, so make sure that you give your best effort, okay? So moving ahead, infinite series with positive terms, okay? So infinite series and its convergence and sum, okay? So yeah, let un be a given sequence, okay? Then the symbol of the form. So okay, so this is the how we denote sequence. You have studied earlier also. Before this chapter, you have studied about sequence. So un here is a sequence. A sequence is nothing but a value from natural number, a function from which maps from natural number to real number. That is real number sequence. Okay, since we are studying real analysis, so we are talking about real numbers only. So suppose we say that un is equal to 1 upon n square. Okay. So the sequence here would be, what we see if we put n equal to 1, we get 1, then 1 by 4, then 1 by 9, then 1 by 16. So it is nothing but here we put f for n equal to, we take natural numbers, and this maps a function into a real number. It is 1, 1 by 4, 1 by 9, 1 by 16. So this was sequence. In the earlier chapter we have studied about this sequence. Now today we will study about series of infinite terms. See, suppose un be a given sequence, then the symbol of the form, what if I say we have to add this 1 plus 1 by 4 plus 1 by 9 plus 1 by 16. Okay, so un plus dot 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 n, this is called infinite series of this sequence. Okay, so that was a sequence. If we write this in a sequence, then it is a sequence. But if we add these numbers of or the elements of those sequence, then it is called series with infinite terms. That is for n equal to 1 to n equal to infinity. Okay? Suppose if we, in this case we have to take the summation un, that would be 1 plus 1 by 4 plus 1 by 9 dot 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 to, this will go on to infinity. Okay, to the given sequence we undermine the liberator. Okay, now if Sn denote the sum of the first n terms, okay, we calculate this Sn, okay, or Sn is also called the partial sum. Okay, Sn is also called the partial sum. So if Sn denotes the sum of the n terms of infinite series, the sequence is of partial sum of the series. This is called to be partial sum. Okay, since summation un is from u1, u2, ut dot dot to infinity. Okay, but in the case of Sn, which is the partial sum, we take till un. Okay, and when we say that a series is convergent, we actually want to say that this sequence is convergent. That is, Sn, the sum of the partial sum, will form a sequence. Okay, I'll explain it here. Suppose we have taken this example that un is equal to 1 upon n square. Okay, suppose we calculate. We need to find summation of this. If this sequence converges, series converges or diverges. So first we take the partial sum. Partial sum, what would be the partial sum? That would be 1 plus 1 by 4 plus 1 by 9 dot dot to n square. Okay, so for every value of n, this itself will form a sequence. That is, if we write S1, okay, then what will be the value? 1. Okay, if you write S2, this will be 1 plus 1 upon 4. If you write S3, 1 plus 1 upon 4 plus 1 upon 9. So this partial sum Sn would itself form a sequence. See, I told you what is a sequence. A sequence is nothing, just a function from natural number to real number. Function will maps from natural number to real number. So what is this? This is Sn. Okay, so here if we change the value of n, we get different value n. So when we say this is convergent, we mean that this sequence is convergent. When we say that this series is convergent or not, we find out that this is convergent or not. That's what we're saying here, that the infinite series U1 is said to be convergent if the function Sn of its partial sum is convergent. That is, limit n tends to infinity. Now, so if limit n tends to infinity, Sn will converge to S. We have studied the concept of limits and sequence. What do we mean by when we say limit n tends to infinity, Sn is equal to S? Then S is called we say it converges to S. That is, see, in this example only I'll show you that when you see the value of this number is decreasing every passing. Okay, so when n would be 100, it would be very less. Well, it won't be adding significantly to the whole series. So when n tends to infinity, there would come a time when the sum would not be changing. It would be a constant term. Okay, so that's why we said it converges to S. And we have studied what does it exactly mean, the clear-cut definition of convergence, that is fx tends to a series tends to converges to L if un minus L mod of un is less than epsilon for any epsilon if n is greater than m. Okay, so that is a whole different thing we have studied in the sequence. Here you can understand that, you can see here, see, I wanted to show you what does it physically means that a series converges to a sum S or a sequence converges to a value U. That is, suppose first we consider the case of sequence. See, in this sequence, when we go on increasing, it will be 1 by 4, 1 by 9, 1 by 16. See, it is decreasing. So we can say that at any point of time, it may converge to 0. It may converge to 0. See, it will be 1 by 25, this 1 by 36. So at into infinity, it will tend to 0. Okay, so sequence tends to 0. So in this case, if we write this example as, see, this is 1 plus 1 by 4. The addition is small here. What is 1 by 4? It is 0.25. The next term we see, it is added by 1 by 9. The next term we see 1 by 60. So at any point of time, there will come a time when this addition won't matter. So when that value comes, that is at n tends to infinity, that is where it converges. Okay, I'll give you an example here. Good example to start with. Suppose I say 1 upon 1 plus n upon n plus 1. Okay, I have to find this summation of this series. Okay, so we could write, if we do partial fraction here, that is, we could write this as, I'm writing it anyway, suppose this is equal to un, okay, n equal to 1 to infinity, n equal to 1 to infinity, okay, where un is equal to 1 upon n plus 1, okay. So can we write this as this? Okay, taking this LCM same, and this would come the same value. So can we write this? Can we write this like this? Okay, so if we have to write, what will be the value of U1? U1 will be 1 minus 1 upon 2. What would be the value of U2? This would be 1 upon 2 minus 1 upon 3. U3, this is 1 upon 3 minus 1 upon 4. So if we write un, this will be 1 upon n minus 1 upon n plus 1. Okay, so if we find the partial sum here, that is the Sn, if we add this, so this would be, Sn would be nothing but u1 plus u2 dot 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 un. Okay, adding this we see that, see all this term would cancel out. 1 by 2 would be cancelled here, 1 by 3. So cancel out, and cancelling all this term, we get the value 1 upon 1 minus n plus 1. Okay, so Sn is this. Okay, it will form a sequence with the general term 1 upon 1 minus n plus 1. And if we take limit n tends to infinity, Sn would be 1 minus 1 upon infinity, that is 1. So we can say that this series is convergent to 1. Okay, so this is convergence. Okay, but sometimes we see that what if it is not convergence, un, the series un is said to be divergent if the sequence of the partial sum un is divergent, or oscillatory if it is oscillating. I'll give you the example here. Suppose here we take the same case which we took earlier. That is, what if I take that summation un is equal to summation n square. That is we have to find where un is equal to n square. Okay, so summation Sn would be u1 plus u2 dot 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 un. This would be 1 plus 2 square plus 3 square dot 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 n square. This is equal to n plus 1 2n plus 1 upon 6. This again forms a sequence here. So if we take n tends to infinity here, we get the value to be infinity. We see that the value of this, noticing this also you can say that the value of this would always be increasing. That is 1 square plus 2 square plus 3 square. See, the first term, if I take the value of S1, see, these are the conceptual things. You will get the methods. You will get the methods, be it D'Alembert's principle or logarithm test, to check that whether it converges or not. I am focusing on this so that you could have the basic understanding of what does it means for a sequence to converge or a series to converge. Okay, so if I take S1 here, we get 1. If I get S2 here, see, we get 5. Okay, if I get S3 here, 4 plus 1, 5, 5 plus 9, this is 14. Okay, suppose if I take S4 also, then we have 1 plus 4, 5, 5 plus 9, 14. 14 plus 16, this is 30. So we see that the sum, see the difference between first is 4, the second is 9, the third is 16. In spite of decreasing, it is already increasing. And we have seen that if n tends to infinity, this will tend to infinity. By the formula also, we can see the pattern also. So when n tends to infinity, this summation would tend to infinity. That means that this series is divergent. This series is divergent. What if I take another case? That is, suppose I take a series that is un from n equal to 1 to infinity, such that it is minus 1 to the power n. Okay, for n equal to 1 to infinity. Okay, so what we see that what will be u1? u1 will be minus 1, u2 will be plus 1, u3 will be minus 1, and u4 will be plus 1, going like this only. So if we find the value of Sn, that is u1 plus u2, this would be equal to if we take 0 n minus 1, if n is even and n is odd. So we see that the series here neither tends to infinity or neither tends to a specific value. In fact, it is oscillating between two numbers. That is, it's sometimes 0, it is sometimes -1. So this is called oscillatory series, not hey. If un is called oscillatory series, yeah, okay. If the partial sum oscillates, see, it is oscillating. For every odd value, for every even value, you get the value 0, and for every odd value, you get the value -1. So this is the whole concept of convergent, divergent, and oscillatory series. Okay. So moving ahead, we have a simple important theorem. You don't need to prove these theorems. I'll tell you which theorem you need to prove in the real analysis section, but these are not one of them. The replacement, the addition, omission of a finite number of terms in a series has no effect on its convergence. Suppose I say that un is convergent. Okay, what if you add a constant term, you subtract some terms, you add some constant terms? It doesn't affect the convergence of the series. It will be convergent. Okay, and the convergence of a series remains unchanged in each of its terms is multiplied by a non-zero constant. If I multiply a non-zero constant, the convergence of series also doesn't changes. Okay, suppose I take a series, a sequence to be. See, if n square is if I say summation 1 upon, I prove this is convergent, then we can clearly say that k times n plus 1 is also convergent, since for k not equal to 0. Okay, and if multiplied by 0, then the whole sum would be 0. Then also it converges, but the whole sum would be 0. Okay, now see, this is what I was saying, and now there is a theorem. This is general understanding. If you understand the concept of convergence, you will have a general understanding. Okay, it says that necessary condition. Okay, one thing must be noticed here, that it is a necessary condition and not the sufficient condition. Okay, so what does it say? It says that a necessary condition for the convergence of an infinite series un n tends to infinity is that limit n tends to infinity un is equal to 0. It is a necessary condition. It says that limit n tends to infinity un is equal to 0. That is the nth term when n tends to infinity. If it is 0, then it is a necessary condition. That means that the series can be convergent or not convergent. But if it is not equal to 0, it is definitely not convergent. It is definitely not convergent. We have seen the case of this example. Take the case of this example. That is what we took, summation n square. If we take limit n tends to infinity, n square, this would be infinity. So it is not equal to 0. So this series will not converge or diverge. But in case of 1 upon n, okay, so if you take limit n tends to infinity, the un would here be 0. That doesn't mean that this would converge definitely. This means that it may converge, it may not converge. But if it is not equal to 0, it is definitely divergent. Okay, so it is a test of checking whether it is divergent or not. Okay, or disprove it. We have to disprove, if in case we have to disprove a question, this question comes in the 10 marker of your UPSC syllabus examination. There is a compulsory question that they have given a very simple, very difficult looking series, but the trick there is that you first check that if the limit n tends to infinity un is not equal to 0, you directly write it that it is divergent. But if it is 0, let's say in this case, limit n tends to infinity, un is equal to 0. In this case also, to 0, but this does not give the whole proof that it will be convergent. See, I told you this is a necessary condition, but not the sufficient condition. Okay, so for this is convergent, by the way, and this is not convergent. This is not convergent, and that is convergent. We will see that what happens after this. If we get the value 0, then what are the methods which we have? What are the tools do we possess so that we can check that if a series is convergent or not? Okay, but this is a very important property, or I would say a condition. That is the necessary condition for convergence of an infinite series is that limit n tends to infinity, un is equal to 0. Okay, in that case also we have taken another case where I proved that summation 1 upon n plus 1, it is convergent. See, you take the limit n tends to infinity, it is equal to 0, and we have proved that it is convergent. But in some cases it won't be the case. Okay, now we have the case here that we have to find that it is divergent or convergent. Okay, so clearly using the, first of all we checked using the earlier formula, that is limit. See, here the un is nothing but under root 3n square plus 5n plus 4 upon 4n square plus 1. Okay, so if we take limit n tends to infinity un, limit n tends to infinity, clearly in the case of limits, we have to study this in intermediate level, that if the coefficient of numerator and denominator are the same, then the value of the limit is the ratio of these two, that is it would be equal to 3/4. Okay, another way, if you have to do it in a proper way, so what do we do here, that if we divide both sides, both numerator and denominator by n square, we get 3 upon 5 upon n plus 4 upon n square, that is 4 plus 1 upon n square. And now if it tends to limit n tends to infinity, this anything divided by infinity is 0, this is 0, this is 0, we get under root 3 plus 0 upon 4 plus 0, this is under root 3/4. Now, the most important thing is here that it is not equal to 0. So this series is divergent. Okay, so whenever you see a question of series, okay, one thing is you must note that there is an infinite series with positive terms. Here we are talking about only the positive terms. Here the un is a positive term. We will have a separate chapter with negative terms also and alternating terms also. But in this chapter, we are this is the most important topic. Okay, this question comes very much in your optional examination. That is with positive terms. Okay, so when we get a series, what do we do first? First of all, whenever you find a series in examination, no matter if it is a 15-marker question or 10-marker question, first of all try to apply this property. You first find out limit n tends to infinity. If it is not equal to 0, mostly I have seen that when they ask a 10-marker question, then it is not equal to 0, then you can directly write it is divergent. Okay, but in the case of 15-marker question, you will get this equal to 0, but don't write that this series is convergent. When you get 0, then you are not sure that it is convergent or divergent. But if you get non-zero, then it is definitely divergent. Okay, so depends upon the question by question. Now here comes an important theorem, I would say. In fact, one of the most important theorem, and this similar theorem we have done in the that chapter also. This one. sequence chapter also, but this time it is principal convergence of series. Cauchy's general principle of convergence of series. See, okay. So necessary and sufficient condition for a series to converge is that to each epsilon greater than 0. Okay. All these things in the real number, which I have taught you earlier also, that is the limits, that is the sequences, and now the series, all have the same value. When you find limit and tensor field, all have the same definition. A necessary and sufficient condition for a series to converge is that for each epsilon greater than 0, for any epsilon we choose, greater than 0, 0.1, 0.2, 1.4, 7, any epsilon greater than 0, then there exists a positive integer m such that if this is less than epsilon for all n greater than m. What does it symbolically, what you should understand here is that, see, I always believe that mathematics is a very doable subject or easy subject if you have the good grasp over the basic knowledge. Okay, so when I was teaching you this earlier on in this class, the concept of convergence and divergence, I told you what it signifies, convergence and divergence. Seeing this property, you will also understand that what happens is that we say a sequence converges. First of all, I change my pen. So we say that a sequence converges if after a specific term m, after a specific term, this m could be 1, this could be 5, this could be 6. For after a specific term m, the summation of other terms. Suppose I take n is equal to 6. Okay, then we say that um plus 2. Suppose I take m equal to 6 and u7, u8, un. Okay, all the rest of the terms will lie inside an epsilon, and this m depends upon the value of epsilon. This m depends on the value of epsilon. No matter, I can like this. I could write this showing that, or I could write it like this, showing that m is a function of an element epsilon. Okay? So if this is, see, after specific m, all the summation lies between a specific fixed number is less than a fixed number, that is epsilon. And this value of m depends upon this epsilon. If in this case only, if you have taken epsilon equal to 6, you may get the value of n to be 32. Okay, so after 32, 33, 34, 35, all the term would be in that epsilon value only, would be always less than that epsilon. Okay, and if you have taken epsilon, suppose another number, say 16, and you get the value m to be 12. Okay, so this would be less than 16, all the term after this would be less than 16. This is how it works. Okay, so now you understand what convergence means. What happens is that after a fixed number of time, that is m, after a fixed number of terms, all the terms would be less than a specific number, that is epsilon. That is the epsilon. So what happens is that is the rest of the term makes it convergent. Since after this m, the whole value of this would be less than some specific number, and this m depends upon this epsilon. Okay, so rest of the whole term, suppose if we consider Sn, u1, u2, dot, un. Okay, so suppose that in this case m is equal to 6 till u1, u2, u3, u4, u5, u6. Okay, and by Cauchy's principle, u7, dot, un, this is less than some number epsilon. Okay, and this is a constant number not tending to infinity. This could be easily calculated. So what would happen is that a constant number with adding this fixed number epsilon, so we know that a fixed value will come, and that's why the series converges. Okay, so it is a very important principle. Very important principle. You might be using it, and there has also come a question from, I think, UPSC 2021. Okay, 2021 or 2020 in the compulsory portion, where one has to use the Cauchy's principle of a series to prove that question. Okay, so you have to understand that a necessary and sufficient condition, it is both necessary and sufficient condition for a series to converge is that for each epsilon greater than 0, there exists an positive integer m. See, this is depends on the epsilon. Okay, so positive integer m such that all the terms after m are bounded with an upper bound or lower bound. In the case of modulus, this is bounded both sides. Okay, if you remove this modulus, it will be bounded both sides. So that this number is bounded after a specific term, the whole series is bounded. It has to lie between a fixed number, that is the epsilon, and the other terms which are constant, which could be added, and we get to know that series convergent or divergent. Okay. This is a very important theorem, and it is also in the sequence part also, it is also for the series part. And this whole concept that a necessary, what does a limit means, or what does convergence mean, is to understand this whole concept. This whole concept. That is, every value lies between is bounded by a fixed number after a fixed interval, fixed number of terms, that is m. This m could be 6, this could be 36, this could be 106. But after 106, the terms would be fixed. The summation would be bounded both sides. So that series is convergent. If I can say that, suppose I say that summation un, and I say that after a fixed term, it is um in this case. I'm very much focusing on this concept, because once you get this concept, you get the whole sequence, idea of whole limit and whole value of what does this convergence of sequence and series means. And even in the case of improper integrals and everything, you will get the value. See, if un plus un plus 1, okay, so if I told you that after a fixed number m, the values of the other term would lie between a fixed number epsilon, okay, so this is equal to, suppose I have taken a series un equal to summation 1 upon 2 to the power n, that is, this is 1 upon 2 plus 1 upon 4, this is 1 upon 8 plus 1 upon 16, 1 upon 32. See, if I say that after 3 digits, that is after this m equal to 3, this 1, I say that this whole would be less than, say, 2. I say it is less than 2. This is less than 2. It is less than 2. When we calculate this, we get the value less than 2. Okay, so if I say that this is less than 2, so can we say that this is a convergent? So if it is less than 2 and we get the value to be this, okay, so we can say that this whole series is convergent. We will get the specific value. Since this after terms, after m equal to 3, the value of this will always lie between less than 2. So all you have to do is calculate till 3. See, calculation would come in your examination, that you have to calculate the summation of the series. The question comes whether it is convergent or divergent. Okay, so one should have the clear understanding what is convergent and what is divergent, and how this theorem works. You don't need to prove this theorem, but you need to understand one thing, that what does this theorem mean? This theorem says that if after a fixed number of terms, if all summation of all the other term is bounded, then the whole series is bounded. Okay.